Okay, all right. So let's take a look at the example. Okay, so we have an ideal gas is taking from A to B on the PV diagram. Okay, so we use a lot of PV diagram, of course. And then during this process, is 700 joule of heat is added and the pressure doubles. Oh, all right. Which is, you can see from the PV diagram, the pressure is double. So that means, actually, I can just note it right here that this is 60. Okay, so that is 60 in the unit of kilopascal. All right, then. Now, the questions, all right, there are three questions. How much work is done? What do you think, guys? I don't know, you already up for questions. It's like, well done, is still early. All right, but we already, okay, in the physics mode here. Okay, so first of all, this is an easy one. Remember, the work can be seen from the area under the curve in PV diagram. So in this case, there's no area under the curve. It's a vertical line process, so there's no, the area is zero. So the work done is also zero. So there's no work done by or on gas, no matter what. Part B, how does the temperature of the gas at A compare to its temperature at B? All right, so if you still sort of remember vaguely, we already discussed about whenever you have a PV diagram and then you combine it with the PV equal to nRT, okay? And when you fix the temperature, so it means you are considering the constant temperature process. So it means the whole right-hand side is a constant, okay? So that's mean the PV curve will look like this, okay? All right, so if you flash back a bit, so like a dashed line that you see here, when you have a PV curve that is like the product between X and Y equal to constant, then you can have this one. We remember we call them the isotherm. Okay, so it's a constant temperature line. Think of it that way. And then of course, if you go higher in temperature, this line will go upward. I mean, it's actually diagonal up to the right. Okay, so I will try to use that idea here. So it means I can imagine that in every PV diagram, you always have this isothermal line sort of overlay on top. Yeah, sounds good. All right. So from here, you can see that at least this is going to be the low temperature. This is going to be a high temperature because the higher lying isotherm means a higher temperature along with it. So going straight forward up from A to B, it means you jump from a lower isotherm to a higher one. So that means definitely the temperature will increase for sure. Okay, so at least you know this is higher. T at B is going to be greater than the temperature at A. All right. Well, the good thing for this one is they haven't asked about what is the temperature, but if you really want the numerical value of the temperature, you can compare the states at point A and point B by using a simple relationship of the equation of state. So let me use A and B. PAVA over TA equal to PBVB over TB. Okay, you guys with me? Okay, because PV over T is always a constant. Because it's a fixed amount of gas, the R is just a constant. So over here, PV over T is just N times R. Cool. All right. So in this case, okay, so let me note this is part B. So volume is constant, so you can cancel the V out, and that's it. So you know the ratio between the pressure and temperature. Because the pressure is doubled, the temperature will be doubled as well, if you like. Okay. However, they didn't say what is the temperature at point A, for example. So you don't know what it is, but at least you know that the temperature at A will be half of the temperature at B, something like so. Okay, sounds reasonable. Okay, not too bad, yeah. All right, part C. How does the internal energy of the gas at A compare to the internal energy at B? Of course, it's followed from part B because we know, okay, let's remind you what we have over here. U equal to 3 half nRT or 3 half kNT. Okay. All right. So this is sort of like a straightforward relationship between the internal energy U and the temperature. We already said the temperature will tell you the total amount of energy in the system. Okay, so the bigger the T is going to give you the bigger of the U. So in this case, actually, you know exactly what's going on. The temperature is twice as big. So the internal energy will be twice as big as well. So actually, you know, U at B will be greater than U at A. Or actually, you can say U at B will be twice of the total energy or the internal energy at A. All right, sounds cool. Not too bad. Kind of like remind you things a little bit. All right, coming back slowly. Okay. All right. So for those of you that are concerned, I'm not sure you guys are concerned or not. Just a quick announcement about the homework because we kind of like sort of slow going. So don't worry about the due date on the homework. I already told Ajahn Tane that actually you can submit your homework. Well, of course, beyond the due date. That is fine. Right? Just make sure that you submit it. Okay. All right. So you kind of like, okay. Some of you probably confused. Ajahn, we haven't studied this. How can they do that, do this, problems, on and on. So, all right. So until we catch up, all right. But at least don't worry about the due dates. Okay. But well, don't make it too late. All right. But just make sure that you submit the homework. Okay. All right. Any questions, guys? So sort of bring back memory a little bit 2 weeks ago. All right. We'll have some more. Okay. I don't know if you guys do. I hope you guys nod your head and then, okay, get going. All right. This one is a little bit more sort of like quantitative. Okay. And it's going to take now sort of a little bit more detail in calculations. Okay. So start with the PV diagram once again. You have a series of thermodynamic processes. You're going from A to B. So let's go A to B. And now you say that is 150 joules of heat is added to the system. All right. So just to show you what, I mean, there is some heat involved in this process, I can sort of draw like an arrow or something like this. But this one might look a little weird because, well, Ajahn, why you go from left to right on and on, we'll have a better explanation today. But for now, just like this is like a personal note saying that there is a heat coming in 150 joules. Okay. Now process B to D, there is a 600 heat coming in, 600 joule of heat. All right, just note on it. So it's just right on top of the PV diagram. I mean the line or the curve in the PV diagram. Now the question asks you to find the internal energy change during process A to B. Okay, let's take a look. How are you going to do this? Right, this is getting more sort of like detailed. All right, first of all, you're going from A to B. So think of A to B. You have only 3 terms to consider in first law of thermodynamics. You have the U, the Q, and the W, correct? You have only 3 things. But because from A to B, you can see that the simplest way to get to this one is just start from the work, because you can see right away from it, there's no work. Okay, no area under the curve. So that's done. Second one, the easier one is, I mean, you already know that the Q during this process is already given. You don't even have to calculate. So that's good. You already get the 2 components in the first law of thermodynamics in here. Okay, so that's it. From the first law of thermodynamics, delta U equal to Q minus W, and that's it, 150 joule as well. And it's positive because the heat is in, so you can sort of put a positive sign there just to confirm that the change of the internal energy is up, is positive. Okay, sounds good. All right, now let's try part B. Okay, part B now, they want to go further. They go from A to B and then they go from B to D. So that means you have to consider what is going on from B to D as well. So in this case, just to distinguish the delta U from each sub process, you can put like a subscript in there. Delta U on the part, in the part A, you can say it's a delta U AB if you like. Okay, so what we are trying to do, I mean, you can put subscript on anything if you want to. Okay, just to distinguish between sections. All right, from B to D, we probably going to try to do the same way. So we start from the work because that's the easiest one to get to, just the area under the curve. All right, and that is just, okay, let me give like different color here. Here we go. Just the rectangular area underneath BD line. Okay, so that's it. So it's going to be the width times the height. Okay, it's a P delta V. All right, go ahead. P delta V, the width times the height. And you think about it, is it going to be positive or negative? You guys say, okay, it's going to be positive because the volume is increasing. You're going from 2 to 5. So you're going to get positive work done. Gas expands, volume increases. Okay, cool. All right, so let's get going. The P is 8 times 10 to the 4th Pascal. The volume change, you go from 2 to 5. So you get a positive volume change of 3 times 10 to the negative 3. That is a cubic meter unit. So let me put the unit in there. Here we go. All right, that's it. So that's the work done by the gas. I can calculate the number a bit. Okay, here we go. Nice. All right, and just to emphasize that it's a positive work, you can put a positive sign there if you like. Okay, what else do you know? Of course, you already know that there is a heat added during B to D process, another 600 joule. So the conclusion is that delta U going from B to D is going to be Q minus W. So it's going to be 600. Subtract out the 240 that we just got. All right, and that's it. You're gonna get 360 joule, but it's still positive. That's good. Okay, and that's it. That's done. Isn't that cool? All right, and once again, just want to confirm the idea that I have sort of in your head. Don't forget that you can always think of isothermal line in here all the time if you like. See, that's kind of something like this. So it's me going from A to B, you sort of know in your head the answer is supposed to be positive change in the internal energy. And that's what we got. Internal energy increases 150 joule. Going from B to D, you also jump to a higher isotherm. So you know in your head, the answer is going to be positive change in the delta U. And that's what you got right here as well. Okay, cool. All right, now let's try part C. They say, what is the total heat added in the process ACD? Now they don't want to go the same path anymore. They don't want to go A to B to D, but they want to go the bottom route. You want to go from A to C to D. All right, you want to go from A to C to D. They say, what is going to be the total heat added? You want to give it a shot? Do I have, okay, I ran out of space. Okay, you want to try that? Okay, you guys try it. I think it's a good exercise here. I'll give you like a few minutes head start. Okay, let me sort of erase some of these. Okay, so it's clear up things. All right, you want to go from A to C, C to D. But now they're asking you to figure out the amount of heat added during this process. That's what they want. That's what they want. Want to try? A to C to D. They want to find the heat. From what you have seen, it seems like we seem to attack the work first because it's easy once you have the PV diagram. The work is area under the curve. So we still try that. So let's do that. Let's figure out the work done from A to C to D. How much you think you're going to get? Of course, it's going to be area under the curve. So it's going to be this area right here. You guys with me? A to C. Because C to D, you get no work. So what I'm seeing right here is the work going from A to C to D is just that area right here. WACD. Cool. Alrighty. All right. So just to be clear, it's going to be the work done from A to C plus the work done from C to D. But this second term goes to 0. And that will be just the width times the height. Okay. So the height is 3 times 10 to the 4th Pascal. Very good. The volume change, once again, is still positive because you go from 2 to 5. So it's still positive 3 times 10 to the negative 3 cubic meter. Very good. Let's get going. I mean, this calculated number, 90. Okay, you guys check my numerical calculations too. Okay, all right, 90, good. So that's a work done from A to C to D. And if you want, you can still just add positive sign to it. Yeah, what else do you know? What do you think? Very good. I think some of you start to see how to get to that. You want the heat, right? You want the Q. So there is another party that you have to figure out is the what? The W is done. Yes, the delta U. If you know the delta U going from A to C to D, then you can use this combined with the work from A to C to D, and then you can calculate the heat. The question is, do you know what is the internal energy change from A to C to D? And I think that is the purpose of this exercise. Remember, the key features of the internal energy is what? It's path independence. It's path independence. So that means I don't mind which directions, which path you want to take from A to D. The delta U must be the same. So that means you're going along the upper route over here, get to D, or you want to go from, this is going to be, okay, all right, I'm just saying. You go from A to B to D, you end at B. Or you want to go from A to C to D to end at B. As D, the change of the internal energy will be exactly the same. So what I'm saying is going to be the same as you go from A to B to D. Okay, guys, with me? All right, and that you already calculated. That you go from A to B, this is delta U. Okay, let me call this number 1 here. And this is number 2 right there. Okay, so that means it's going to be the total change of the internal energy from 2 sections, from A to B, and then from B to D. Same thing. So that means the internal energy change will still be the sum of these 2. Okay, so it's going to be, how much is that? 510, is that right? Okay, here we go. Okay, you guys follow so far? Looks good. All right, and that's it. So you know W, you know the delta U. Now I can just give you a final answer. So the Q is just use the first law of thermodynamics, of course, is a delta U plus W. I just moved negative W to the same side as a delta U. So it's going to be 510 joule plus 90 joule. And that is a 600 joule. And as you can see, it's positive. That's fine. So that means the heat is added into the system. 600 joules. Done. Okay, there is a question comes in about the work from C to D is 0 because, because it's a vertical line. So there is no area under the curve right here. When you look down, a vertical line has no area beneath it. Okay, you need something, sort of something that shade. Think of it like there's supposed to be like a shadow casting below the curve, something like that. Okay, all right, that is another questions. Okay, let me read the questions. All right, you go back to part B, the 150 joules of heat in the process, not anymore. Yes, okay, so that's a good question. So you can see that the 150 joules was added during A to B, okay? So when we move on to analyze what's going on from B to D, the only thing that's involved in this process is going to be this 600 joule of heat. So the 150 joules is already done. Okay, so you don't need to take 150 joules into your calculation anymore. Or you can think of it like this is an actual process that go on with time. So it's like the system will go from A to B first, right? So let's say in the first path, in the first time interval, and during that time interval, there is an incoming 150 joule of heat. And then after that, you go from B to D, another sections of your process or whatever. And during this process, you have another 600 joules comes in. So that's why when you do the analysis from B to D, that 150 joule is already, it's already done. Your calculations or your analysis is already done in the past, something like that. Okay, I hope this answered the questions, yeah? All right, cool. All right, sounds reasonable. Sort of, you start to see how the first law of thermodynamics is sort of like, revolve around these three quantities: the heat, the work, and the change of the internal energy. So three things going around. Okay, all right, we still have some more. All right, try again. All right, this is a good warm-up thing. All right, one more, guys. Actually, this one I have more space. Okay, so I know we have space to write. Okay, all right, you guys try this. Okay, let's work on this together. I think this is a good sort of like a workshop style. You guys sort of try to calculate on your own tablet or your own desk or table or whatever. Okay, the graph in the figure shows a PV diagram of, now you know exactly it's a 1 mole. Very good. So that's N, small n. That's good. Now from part C to A, C back to A, is isothermal. So that's good. So that's mean this A to B is already isothermal process, and it must be lying on an isotherm. Okay, I think I have to do it like this. Isotherm. Very good. All right. And if you like, once again, if you want to imagine that there is always an isothermal line everywhere in PV diagram, you can draw another line through B, through point B if you want. Okay, now here comes the first question. Find the pressure of the helium at point A. Let's start from this one. It's not thermodynamics just yet. It's just the state of the gas. And they haven't asked about heat, about work, about internal energy. They just asked, what is the pressure at A? What do you think? All right, so if you want to calculate what's going on at A, the easiest way to do is just pick a point where you know information already, or whatever points that you know exactly what to do. So when I look at this one, it's like, well, point C is nice because point C, you know the pressure, you know the volume. Okay, that's kind of good. And when you come to point A, you want to figure out the pressure right here. So let me put here is a P sub A if you want. Okay, so I'm going to compare between point A and point C. And you know from the equation of state, PAVA over TA equal to PCVC over TC. Sounds good from gas equation. And because A and C are lying on the same isothermal line, they're sharing the same temperature, so this can be canceled. Okay, TA equal to TC. T sub A equal to T sub C, yeah? Very cool. So let's make it simple. The product between the pressure and volume stay constant. And because, here we go, from C back to A, the volume decreases 4 times from 0.04 to 0.01. So of course, the pressure has to compensate by going up 4 times as well. You guys with me? Because the product has to be the same. Okay, so actually I can say right away it's going to be 8. Done. So you know exactly what is the pressure at point A. Very good. All right, let's try part B. Okay, just let me know if there is any point that's still unclear. Yeah. Part B, find the temperature. All right, they want to figure out the temperature of all points A, B, and C. That's fine. Let's attack. Now you can attack A or C because now they're sharing the same temperature. So let's look at A. Once again, PAVA equal to nRTA. That's equation of states. Now you know the pressure, you know the volume, you know the N, you know the T. So I can say T at A is going to be PAVA over N times times R. Now I can plug in the number. So it's going to be 8. But the unit, you can look at it, is like 10 raised to the 5th power. So I will have to say 8 times 10 raised to 5 Pascal. The volume at A is 0.01. It's already in cubic meter. That's nice. Very good. Divided by, of course, the number of mole is given to be 1. All right. And then you only need to substitute the value for the R. However, I just want to leave R in there because we can always punch the calculator later. But for now, that's good. All right. And this gives me 8,000 over R, I hope. Yeah, is that right? Yeah, 8. Cool. And this is going to be the temperature at B as well. Oh, I'm sorry, at C as well. Because A and C are on the same isotherm. Now you already got temperature at 2 points. Now you need to figure out the temperature at point B. What do you think is going to happen? You're right. Ajahn, we have only one relationship to use here. Now you can pick any points now because you know all the information at point A and C. So if you want to go to point B, you just compare B and pick a point. I can pick A, for example. So PAVA over TA is going to be PBVB over T sub B. Yeah. And now when you compare A and B, the good thing is they're sharing the same pressure. They're lying on the same pressure. It's an isobar, A and B. So the pressure at A and pressure at B is the same. I can just cross them out. So now the ratio between the volume and the temperature has to be fixed. But now you can see that go from A to B, you increase the volume by 4 times from 0.01 to 0.04. So the temperature has to go up 4 times as well. You guys with me, yeah? So the temperature at B is going to be, right, for clarity, I can just say it's a BV over V sub A times T sub A. But the volume at B divided by volume at A is 4. So it's a 4 times the temperature at A. And that is going to be, I just multiply 8,000 by 4. It's going to be 32,000 over R. All right. The unit will be, of course, Kelvin. It's an absolute temperature scale. All right. And that's done for part B. Now, I think the toughest part is part C. Okay, you can think of part A and part B to be just equation of state application. You just apply gas law. It's an ideal gas, so PV equal to nRT, and PV over T stays constant. Now, the question regarding the first law of thermodynamics is part C. How much heat enter or left the gas? So it means they want to find the sign of the Q as well. During segments A to B, B to C, C back to A. So they all need all segments. All right, let's give it a shot. All right, do I have more space here? I saw it how much? Okay, so I think I'm gonna move on to the next page, all right? Because I know it takes a lot of space, so I add one more page to it. All right, so I'm going to do part C and eventually part D on the next page right here. So part C. So what I'm going to show you, actually, once I'm done with the part C, you're gonna be able to answer part D as well, because part D, okay, let me read it, is the question regarding the find out what is the internal energy change from A to B, B to C, C to A. So, I mean, it's already in the first law of thermodynamics. So what I'm going to do is I'm going to show you like all in one right here, going from each section in your process. I should calculate all three parameters, I mean, all three quantities, the Q, the W, and the delta U already. So I should be able to answer everything. Okay, so I will go C and D all together right here. All right, so let's start from A to B. Let's go from A to B. All right. And I'm going to do just like what we did in the previous exercises. The easiest way is start from the work. Okay. It's just area under the curve. Why not? All right. That's the easy one to go to. So that's go from A to B. The work done from A to B is just area under the curve. Here we go. All right. That's good. So let's do it. So it's going to be the width times the height. Okay, and the width, we already say that this is 8.0. So it's going to be 8 times 10 raised to the 5th. Here we go, Pascal. Okay, times the volume change, the width, which is you go from 0.01 to 0.04. So it's actually positive change in volume of 0.03 cubic meter. All right, very good. So let me multiply. It's going to be, there you go, well, joule. Okay, looks good. 24,000 joule of work. And it's positive, of course, because the volume increases. Okay, what else do we know? Of course, delta U are done because we already calculate temperature at all points. Okay, when temperature changes, the internal energy changes, and it's simply 3/2 nR delta T. Yeah, that's for the monatomic ideal gas. That's the change of the internal energy is going to be 3/2 nR and the change of the temperature. So 3/2, N is 1, R, just leave it as R, and it's going to be temperature at B minus temperature at A, right? The order is important, I told you, right? I've been emphasizing this for a long, long time, right? Right? You go from A to B, the change is going to be B minus A. Okay, take the final points, subtract out the initial points. That's there. You already know the temperature of all points. So let's substitute it in. T at B, go back here. Temperature at B is this much. Okay, 32,000 over R. Subtract out the temperature at A, up top, 8,000 over R. That is a nice thing about didn't calculate didn't really do the numerical calculation of the R. The R will actually cancel out. Okay, and that's good. So it gives you, if I do it right, what? 24, 12, 36,000 joule. Here we go. Okay, and that's it. The heat is going to be delta U. I take the negative W, move it to the other side to stay with the delta U. So it's turned positive W there. And that's it. You just sum these two quantities together, delta U and the W. So the heat during the AB process is going to be 60,000 joule. And it's positive. What does it mean by positive? It means heat enter. Yeah, Positive heat means heat flow into the system. Okay, you guys still in a good mood here? All right, but I hope I'm trying to do this in a sort of systematic way. Okay, I'll try to attack the part of the problems that it seems like you're going to do the same sort of way, pretty much. Yeah. So that's why, as I said, when you do this analysis from whatever point to another point, you get these three terms: W, delta U, and Q. These are the main three things in the first law of thermodynamics. And this allows you to answer the question, what is the internal energy change from A to B? It's already right here. That's for part D. That's done. So from A to B, the internal energy change is positive 36,000 joule. Okay. Oh, and I think I'm just use different color here. Just won't get dirty. Okay. So we just say heat enter. Okay. All right. So you see the sort of the whole idea how things go. So let's move on. Okay, so let me close it out. Try again. Let's go from B to C. Okay, let me use different color here. Go from B to C. Now B to C is nice. What is W, guys? Very good. It's once again constant volume process. It's a vertical line. So I think just like you guys just saw it before, when it's a vertical line, and the volume does not change. When the volume does not change, work done is zero. Okay. Or you can think in terms of the area under the curve. There's no area under the curve, work is zero. What else can we calculate? Once again, we know temperature at all points. So the change of the internal energy can be done as well. It's just going to be, once again, 3/2 NR T at C minus T at B. Okay, final points minus initial points. And once again, I do 3/2, N is 1, R is there. Temperature at C, we already saw it. It's 8,000 over R. Temperature at C is 32,000 over R. There you go. Very cool. Once again, I can just get rid of R. Okay, and it's automatically negative because you go from high temperature to lower temperature. Okay, let me once again emphasize that you have this imaginary isothermal line here. So from B back to C, you jump from a higher isotherm to a lower one. So that means it's going to be reduced in temperature. So the delta U goes negative for sure. All right, and that's it. So I just do the calculations here. Is negative 36,000 joule. There you go. But one thing that you can notice over here, well, Ajahn, it has to be the same number as what you got up here. Okay, you guys with me? Because from A to B, you jump from a lower isotherm to a higher one, but this problem, you have only isotherm. You have only two temperatures. You go from A to B, you go from T to A to T to B, temperature at A up to temperature at B. But then B to C, you jump back to the original temperature. Okay, and we already said the internal energy depends only on the temperature. So when you go up from A to B, you said the internal energy increases by 36,000. Yeah. And then, of course, when you want to jump back, you have to sort of return that energy, right? Because it already increased by that much. But now you come back to the original position, you have to just get rid of that back to the original position. That's why it's negative 3,600 joule. Okay, cool. I hope you see this sort of the specialties of the internal energy. It only depends on positions or the state. Yeah, and because we already confirmed that the internal energy, it depends only on temperature. So when you jump out to the new temperature, but then you want to jump back, the change will be just negative on of the first round trip. I mean, the first half of the round trip, pretty much. Okay, cool. Q from B to C. Now it's just going to be delta U plus W. Okay, and that's it. Just sum these two together. So it's going to be 36,000 joule. Nice. All right, very nice. Okay, I hope you guys still follow. Let's go to the last section of this. I'm going to do C back to A. Okay. Now, the nice thing about this C back to A, let's attack the easiest one. In this case, C back to A is isothermal process because they are lying on an isotherm. Definitely delta U is 0. No temperature change. Done. That's what thing. One's down. Next, the W. Okay, well, that is the area under the curve right here. But we have already done this back in the time that we introduced the isothermal process. Okay, the area under the curve, we found it from do the integration of that PV equal to nRT when T is constant. And then we get this equation right here. And of course, this equation will be supplied to you in the exam paper. So you don't, if you don't want, you don't even need to memorize it. That's fine. So the work done during isothermal process, it's nRT log V final over V initial. Perfect. Use that. You don't have to recalculate anything anymore. So it's going to be equal to nRT, okay, log of, now you go from C to A. So the final volume is going to be V sub A, volume at A. And initial volume is going to be V at C. Here we go. Cool. Nice. Let's work out the number. N is 1, R is R. Temperature. Now you can pick temperature because we know all the temperature. So temperature at A or at C is 8,000 over R. We got it already. And now you take the log of the V final, which is 0.01, over initial volume 0.04. Here we go. And as you can see, it's automatically negative. See that? Because log of whatever in here is going to be log 1 over 4, which is less than 1. Log of the number less than 1, you're going to get negative, definitely. Okay, and once again, R cancel nicely. So it's going to be negative 8,000 log 4. Just leave it there. Okay, I just turned log 1 over 4 to negative log 4. That's all. Okay, and that's it. So once I'm done with this, I can answer the question about the heats. Heat is just a sum between delta U and W. So you just add these two together, but because delta U is 0, so that's it. Done. So as you can see, if I keep doing this, like any sections in the process, I just say, what is the W? What is the delta U? What is the heat? I can answer anything. Just ask it. I mean, what you want. You want the internal energy change. You want the heat flow. You want the work done. You want, you know, is it the gas or the system perform itself or somebody else compress it down? You know it, everything, because the sign and the number will tell you everything. And that is the first law of thermodynamics gives you. Sounds cool? All right. So I think maybe when you sort of listen to me, it's like, Ajahn, you keep sort of, you know, circling around these words and that's what it is. All right. And then I'll keep repeating things, keep writing the same equations, keep writing the same, whatever well, you can call it like quantities or whatever. But because you only have 3 things to consider. And of course, along with that, the heat, the work, and the delta U, you have equation of state, PV equal to nRT. So it's just sort of like, going in circle right here. But I hope by doing this, a few exercises here, you see how to perform the actual calculations. Okay. We'll have some more today, but it's not going to be a lot more in the sense that you're going to use the same trick right here. Okay, that is a question comes in about from C to A. Okay, so let's focus on this. So the question is regarding this one. I just want to emphasize again. C to A, the problem states directly the process is isothermal. Okay, so when you say isothermal here, it means the temperature change is zero, no change. When there's no change, so it means the AC curve will be on an isotherm. So when the temperature does not change, the delta U will not change. Okay, so I hope you see that the delta U is zero. Key is the delta. The change of the U is zero, not the U. The U cannot be zero. Okay, all right. So I think this is a good question actually. So you have to make sure every time you doing the first law of thermodynamics is the change delta U, not the U. Okay, I think I have seen many people sort of like try to get to the U, and if you sort of forget to put the delta in there, it will be weird, a little weird, because your calculation will turn into like, the numerical value will be a little bit off, and then you seem to get stuck somewhere because, I mean, the magnitude of the numbers that you have to manipulate is going to be different of order of magnitude, something like that. So the key that you have to make sure that you understand this first law is we care only about the change, okay, the change of the U, not the U itself. Okay, so when I say A to C is on the isotherm, that means it's keeping the temperature the same for the whole process. So the U is the same. The U is constant, but doesn't mean it's zero. It's just constant. So no change. Delta U is zero. Cool. All right. Very good. All right. And that's it, guys, in terms of first law of thermodynamics. But why do I have to focus so much on this one? And as you can see, I think I go very slowly in the sense that, I want to go in all detail about doing this, because if you get this basic idea of how to calculate this whole thing, the next subjects that we're going to, and not next subject, is actually just a topic in here, is going to be quite simple. It's not simple, but it's a straightforward extension from this. So let's get to it. Okay. All right, let's get to it. I have to close this one down. All right, let's move on to the topics of this is going to be the next handout. It's heat engines, okay? And actually, this is the only thing we're going to focus today. Even though in the slide, I have entropy and the second law of thermodynamics, but I think this is not going to be in the exam because the entropy is the stuff that takes, it's going to take as long as at least the first law of thermodynamics to study, and it's unfair if I want to squeeze the entropy calculations in like half an hour or something. So don't worry about the entropy and the second law, but don't worry means I'm just going to tell you the story about it a little bit so you get the idea, just in case that you have to deal with it in the future. Okay, especially when the Tenet movie is out. And I think the word entropy is coming out if you guys into the movies, and then sort of like if you went to Tenet and sort of things going backward in time and all this stuff and crazy stuff. All right. So, all right. Well, I don't know, are they related or not, but the movies try to use the entropy stuff to explain how things go in our universe and stuff like that. Okay. But we not get there. We are not trying to get to that point. All right, heat engines, guys. But the point that I'm going to take you to today, definitely, I'm going to tell you the best heat engine in the universe. So after analyzing the heat engines and what does it mean, I'm going to show you the engines that has the highest efficiency attainable to human, or it doesn't have to be human, it can be any aliens that's in this universe. Even Tony Stark or Thanos cannot do any better. Okay. Except that they probably use other technology, not the heat engine. So they get better efficiency. Or maybe they use like Tesla or something, electric, not heat anymore. Okay, let's get started, guys. But you will see today, the reason that I say this one is an extension from what we did in the first law, because I want you to feel like this is not heavy stuff. It's just the same stuff, but it's sort of like the angle of this one is more like an engineering angle, but the behind the scene of this one is still first law of thermodynamics. Let's take a look. So what does it mean by the heat engines? So of course, it's like human's dream. Okay, we want to transform, if possible, heat into work. The reason we want that, because now everyone knows if you have a hot part, right? Anything that's hot, okay, and anything that's cold, and then they are close by, you now know that heat will flow from hot to cold. That's no problem. But now we already learned that the heat is the energy transfer. So that means during that transfer from hot to cold region, there is a movement of the energy. So we wish that, hey, I'm going to take some of those energy and turn it into something useful. And if possible, the best that we can do is, well, Ajahn, it will be nice if we can take all of them. Take them all. If I take them all, that would be nice. You will get 100% efficiency, right? So it means you can now steal the energy that's laying around in this world or in this universe, something like that, okay? But of course, the nature is not going to be so kind to us. We cannot do that. So that means you are not allowed to have 100% heat engine. You cannot take the energy that you have in the nature and turn it into useful work perfectly 100%. That's impossible. So that means some of the heat that you sort of try to draw in from the hot reservoir, you can call reservoir, because that will be like a source of the energy that has a higher temperature. Some of those heat will get dumped out at the colder one, and you only get a part of it. And because everything is under conservation of energy, if I quantify the heat that flow in to be, let's call Q hot, Q sub H, and the heat that you have to discard out at the cold reservoir, and let me call it the Q cold. By conservation of energy, the difference between these two must be the one that you can take out and do something useful. Okay, cool. And because we already know that the heat and the work, they all have the directions. Positive mean heat flow in, negative mean heat flow out. But now we know for the heat engine, you always draw in the heat and discard out. And to make things sort of like obvious that the work done is just the difference between the heat coming in and going out. So I'm just going to take just the magnitude of this one just to make it easier. All right, because we are not trying to do anything weird, because we are focusing on the engine. So that's why let's put an absolute sign in it and say the amount of heat flow in, take out the heat that you need to discard out. That must be the work done that you can take it and use it for something else. Okay, guys? Just to make things sort of like, realistic, the heat engine that's sort of closest to your everyday's life is just heat engine in car. That's it, internal combustion. Okay, and you can see that engine try to do the work. What is the work? I mean, you want to drive that transmission and all the wheel and all the stuff. You want to turn the wheel, get the car going. And the source of energy is just the combustion of the gas. That's why you have to combust the gas into a high temperature. So you hope you get the hot reservoir. Okay, and you use that one, you ignite the gas, bam, you get the heat reservoir, hot, high temperature, and that energy will sort of drive or use all the stuff to drive the wheel and all the stuff. But then you still have something left out. That's why your car will get hot. I mean, because that is the heat that coming out from the engine, and that is a discarded heat. Okay, sounds good. All right. So if you have a car engine that run like 100% efficient, it means the engine will feel pretty much like room temperature. Right? You can touch the front of the trunk and all the stuff. The front of your car. Under the hood will feel normal. It's not hot at all. But everyone knows under the hood, at the heat, at the engine itself is hot when it's running. Yeah, so that's why there is always some discarded heat coming out from the engine. Okay, sounds good. All right. However, there is one more thing I want to add right now. Because you want the engine to run continuously. All right. So it's not like a one-way trip or anything. It's just that it's gonna be a round trip. You just keep running. So that's why you can see the cylinders and everything inside your car engine. It has to run back and forth, back and forth, back and forth. So you are looking at a cyclic process. So you want something that run in cycle. Okay. But the nice thing about coming back to the original position in cycle is there will be no internal energy change. Isn't that nice? Okay, because the internal energy change is zero when you come back to the original position. Perfect. So delta U is gone for every cycle. So that's it. So you know exactly the amount of work that you're going to get from your engine is just the difference in the heat that we saw over here. Okay, sounds good. All right. And that's what will be the key things that we're going to do here is efficiency. How can we figure out the efficiency of an engine? Okay. So the efficiency is simple. The concept that I sort of keep in mind all the time is just what you get over what you have to give. All right. Right. What do you want to get? I want to get the work done. I want to get the W. Okay. The bigger the W, the better the better the efficiency. What you have to give here, I have to provide this hot reservoir. I have to combust, ignite the gas, combust the gas, release out the chemical energy, all the stuff. So this is what you have to provide to the engine. So what you have to give is a Q hot. And that's it. This ratio will give you the efficiency. Okay. All right. And of course, you know that the work done is just the difference between the Q hot and the Q cold. You can sort of manipulate this equation a bit. And you say that efficiency is just 1 minus Q cold over Q hot. And as you can see, the efficiency is the number that go between 0 to 1. Okay. And if you want to turn into percent, it's like a percentage. You can just multiply by 100 if you want. But for the number itself, if you have a 0 efficiency, mean you don't get any work done at all. So that's 0% efficiency engine. But if you have efficiency of 1, that means you can turn everything into work. And the way to achieve that is here. You have to turn this into 0. No discarded heats. If you can achieve that, that is 100% efficient engine. All right, cool. Or maybe you can say, Ajahn, there is another way. I can take this Q hot to be infinity. Like, okay, if you can find that, super hot, then the efficiency will be approaching 1. But you cannot do that. Okay, that's not practical. Okay, all right. And just a quick numbers, the engines in your car, even the diesel engine or the gasoline engine, the efficiency is only like, the good one is like 40% or so. So every gas that you burn, right, you only take amount of energy out of it only like 40%, and then you throw away more than half. Okay, that make your hood in front of you or in the back of your car a little sort of, it's not a little, actually it's very hot. Okay, you throw out energy a lot. So we're going to turn electric, I'm pretty sure, right? Eventually, because the electric car, I think the efficiency can go up to maybe 80 something, 90 something percent. So that's better efficiency. All right. And from what we have up to this point, I think the internal combustion engine will disappear very soon. I would say in a decade or so, right? Things will change. And especially when the Tesla and all these people, the Volkswagen and all this stuff is pushing for the electric. China, of course, definitely. So I think things go fast. All right. So I think in a decade, I think you probably, do more like electric. Okay, so let's take a look at a quick example here. So you have a gas engine burn 0.2 gram of fuel and deliver 2,000 joules of work per cycle. So this one will give you the overview of what things goes. Given that the heat of the combustion is 5 times 10 to the fourth joule per gram, what is the heat that you need to discard each cycle? And what is the thermal efficiency? Right? Just sort of get the idea of the efficiency in. So usually I can refer to the diagram. I think this is a good one all the time. You have flow in heat, Q hot. You have the discarded heat, Q cold. And you want to deliver some useful work. That's the key sort of like diagram for the heat engine. Okay, because they already told you that it can deliver 2,000 joule of work. So that's good. W is 2,000. Okay, and now you have to burn 0.2 gram of fuel. So it means what is going to be the energy that you get from burning 0.2 gram? You will say is going to be 0.2 gram times 5 times 10 to the fourth joule per gram, right? Because you know each gram you get this much. So you only take 0.2, you multiply 0.2 with that heat of combustion. So you get 10 to the third joule, 10,000 joule. Oh, sorry. Yeah, is that right? Yeah, 10. Well, is that right? 4. Sorry. Okay. Sorry. That's kind of small. Here we go. So you get 10,000 joule of Q hot, and Q hot provided by that gas engine. I mean, that gas burning. All right. So now you can see right away, you come in with 10,000, you only make 2,000 useful work. What will be the rest? It's going to be 10,000, subtract out the 2,000. You guys with me? So it's 8,000 discarded heats. So what should be the efficiency, guys? What you get over what you have to give or provided. There we go. And that's it. So this one is 0.2 efficiency, or you can say it's a 20% efficient engine. Okay, all right. So I hope you see the overview of what it means or what it's supposed to be, sort of the numbers that give you the idea of how well this engine will run. We use efficiency. All right, but it's about heat, right? So that's why it's just an extension of the first law of thermodynamics. It's a good application, actually. Okay, let's take a look next. All right. I mean, on passing, all right, even though I don't want to sort of give you like, you know, some sort of like too much stuff to take, but this is something that, once again, we use it every day. What if I want to do this in reverse? All right. Everyone knows heat will go from hot to cold naturally. But what if I want to go backward? I want to take heat from the cold place to the hot place. How would you do it? Of course, you have to reverse everything. So you're not only you're going to get something out, you have to give something to the pump. To the engine. Okay, so that's mean now you have to reverse the direction of the W. So instead of the engine perform works for you, you have to do something for the engine to make the engine run in reverse and can draw the heat from the cold place to the hot place. Do you know what kind of engine is this? Very good. That's your refrigerator, right? Okay, or air conditioner. So in this room, it's cold, pretty much. Let's say 25 degrees Celsius. Outside is hotter, of course, maybe 30, 35 Celsius. So what air conditioner is doing is taking the heat from the inside the room and dump it out outside the room at the hot coil outside. Okay, so actually the air conditioner and the refrigerator in the fridge is cold. Outside the fridge, let's say in the room, is hotter. The refrigerator is trying to bring the heat from the inside of the container, the freezer, whatever, and dump it at the back of the fridge. Yeah, sounds good. Okay, so air conditioner, refrigerator is the heat engine runs in reverse. However, when you say the reverse, there is one property that work the same way in mechanics. Water or objects drop from high to low. If you want to pump the water from low to high, and I say pump, you have to pump the water. You use a water pump. You pump the water from the lower level to a higher level. So over here, it's the same idea because you want to take the heat from the lower temperature to a higher temperature. It's sort of like against the nature a little bit. So you can call this engine the heat pump if you want. Okay. However, no matter what you're trying to do, it's still under conservation of energy. So you can see right away the Q hot must be, of course, there is a Q cold comes in and there is a work done that throw into the heat pump. So the sum of the two must be equal to the energy that delivered to the hot reservoir. Yeah. So I hope you see that the idea is simple like that. But the idea is still simple in the sense that if I want to see, hey, Dan, what is the efficiency of this pump? How good is this pump? Is this a good pump or is this a bad pump? Like air conditioner, right? When some days, right, well, Dan, air sia, yeah, the air conditioner is bad. You're not making the room cool anymore. So that's low efficiency, yeah, something like that. So what you do is you calculate the same logic, what you get over what you have to give. But for the pump case, what do you get? I need to get a lot of this. I want to pump out. Okay, just like a water pump, you want to pump the water from, from the lower level to a higher level. How good is the pump? I want to know how big, what is the amount of water that you can pump up. Same idea. So what you want to get a big amount of Q cold. What you have to provide or what you have to give? Now I have to give the W. See? Okay, so it's still the concept of efficiency. It's still the same concept of efficiency. Okay, but this is the efficiency of the heat pump. So the point of attention, your attention is sort of focusing on Q cold over the W. And because we want to reserve the word efficiency for an actual efficiency, which run from 0 to 1, the numbers between 0 to 1. But this ratio over here, QC over W, can be any number pretty much. It doesn't have the range from 0 to 1. So we don't want to mix up with the efficiency meaning. So we call this the coefficient of performance. Okay. But I mean, in your head, it's the same idea of the efficiency. But we just keep the efficiency for, yeah, the efficiency higher than 100 is kind of weird feeling. All right. Okay. However, this one, you're focusing on how this air conditioner can cool the room, right? So that's why we add the word cooling mode into here. Because of course, in some cold country, in cold region, they might use heat pump to pump heat into the house, into the building. You want to make the building sort of warm. Your attention might be the Q hot, not the Q cold. So in that case, you can do, okay, let me put on the side, but this one isn't, I'm not focused too much on it. If I do Q hot, sorry guys. So let me put on the side over here. If you do Q hot over the W, this is also COP as well, but it's a heating mode. Okay, this is the heating mode. There you go. All right, just so you know. Okay, but I think what is closer to us in Thailand is going to be the COP in the cooling mode. All right, and for the heating mode, actually, if you want to sort of warm up the house and a little bit, you can use like a fireplace or something. You just burn something out. You don't need to operate with the pump or anything. Yeah? Just say, take the, I don't know, burn something or use something. Make things hot is kind of easy. Okay. Make things cold is a little bit harder. Okay. All right. Cool. All right. I hope this is fine. Just, okay. Overall, in conclusion, it's just efficiency. This is a definition of efficiency that I just want to add on top. Now here comes the main discussion that we're going to have to do. All right. I'm going to take you guys to the best engine in the universe. All right. And to get there, there is one more thing that I need to discuss is about the reversibility of the process. All right. Just listen to me a bit. I don't know, is this good or bad? But once again, I want to go back to this example. Right? We did this a little bit briefly in the isothermal process and introduction of the heat, the work, and the internal energy change. But we're going to do this one more time. Here we go. You have a gas in an insulated container. Okay, once you see this, I can say right away there's no heat flow. It's insulating. No heat flow in or out. Now the gas is being contained in the bottom half with a membrane, and suddenly the membrane breaks. Okay, so the gas fill up the whole space. I want to ask again, is there any work done in this case? What do you think? You say no. Remember, there's no work because if you put your hand in there or you put an object in there, object. I mean, this gas doesn't do anything. It cannot lift things. It cannot push your hands. It doesn't, you'd feel nothing. So actually this spreading out of the gas does no work. Okay. So with that, there will be no change of the internal energy. So this reminds you everything about the first law of thermodynamics of this process. We call this process a free expansion because it's expand freely without doing anything. Right? But one thing though, if you look at the left and you look at the right separately, they're both sharing the same energy. You guys with me? Because they're sharing the same temperature. No internal energy change. So the first law of thermodynamics just say, you are okay, left or right, right or left, having the same energy, no big deal. But everyone knows you have only one direction to go. It's from left to right. If you want to come back from right to left, you would say, no, impossible, right? That's why we say this is an irreversible process. And the first law of thermodynamics doesn't really give you any directions. But you know, in nature, it has some directions. And this direction is irreversible. Okay, cool. Now, try again with this one. You do the same thing pretty much. You have a gas, but now you have a movable piston. Can move up and down freely. Let's say no frictions or anything. But then if you want to compress the gas a little bit, you do it very slowly, pretty much by imagine that you sort of pour sand into it slowly. Or you can pour like salt, pepper, or whatever. So the pistons move down slowly, just a bit. But then if you want to change your mind, but Ajahn, I want to sort of expand the gas back, you can just pick up those sands and hopefully slowly it can just expand back. In this case, it looks like if you do things sort of slowly, it seems to be reversible. Okay, and now you start sort of notice something here. Well, hey, Ajahn, what you have done in the past, we use PV diagram. And you have a process going from A to B, B to C, C on and on, whatever you want. And we can always switch the direction of the arrow at your will. You can do it anytime. You can say, this is an sort of go up and then turn right if you want. But then we'll say, Ajahn, I don't want this. I want to turn back. Okay, fine. You just reverse the arrow and you have a reverse process. So as you can see, things that you can do on the PV diagram represents a reversible process. You guys with me? Okay, so things that you can draw in the PV diagram means you know the pressure, you know the volume, and you know how this pressure and volume changes. So that's why you can draw a curve in the PV diagram. So once you know that exactly, you can pretty much take things backward. So it seems like the process that you can draw on the PV diagram, that is going to be a reversible process. But now you start to know, it's like, oh, Ajahn, to get this, I have to imagine this. And is it real? No, right? In real life, you're never going to be able to do things super slow and get things done. That's impossible. So that's why I can say with confidence that every process in this world is irreversible. With me, guys? Okay. But it seems like in physics, we have to start somewhere. So we start at thermodynamics. We use ideal gas, and then we use PV diagram, and we use a reversible process to study first law of thermodynamics. But in reality, I don't think things can be reversed. Okay, so as you can see, if I have a cup of hot water, you sit it here, it's gonna cool down to room temperature. And everyone knows the hot water, once it's cooled down, it's never gonna get hot by itself again. It's done. It's irreversible. Yeah, you guys with me? Yeah, it's not hot anymore. Okay. You're getting older. You're not gonna get younger. That's irreversible. Okay. So whatever your beauty products that you use and say that, hey, give back your youth again, that's gonna be against the law of thermodynamics. All right. But then toward the end of today's lecture, you're gonna see that at least you can do is you probably can preserve that. Okay, not get old too fast, but it's still irreversible anyway. Okay, so what's the point of reversibility? Okay, the point is this. Now, let's take a look at more realistic system. If you have a metal box, let's focus on the top one first. And you're having fun here, I hope. I'm just telling you a story here. Okay, you have a metal box at 70 degrees Celsius. Inside, you have an ice. Of course, it's at 0. You wait a bit, ice melts. The box will cool down. And you probably ends up at some intermediate temperature. Let's say it's at 40 degrees Celsius. You have a water inside, the box cool down. During this process, you have a heat involved for sure because the heat will flow from the box to the ice to melt the ice. Okay. But this process, is irreversible. There's no way that the liquid water will turn into ice. The metal box will get hotter back to 70 degrees Celsius. That's impossible. So this is an irreversible process. But the key point is this. There is a heat involved in this one, right? Melting the ice, cool down the metal box. This heat is gone. You can think of it that way. The reason it's gone because this process is irreversible. So whatever the heat that you use during this irreversible process, it must be one way out. It's already be used up. And because the process will never be able to return to the original configuration, the heat that already involved in this process will not going to be able to return as well. Okay, you guys sort of get an idea, yeah? So that's the heat involved in the irreversible process. Now try again. Now, if I have a metal box now at 0, inside the same ice cube, but then you can see that because they are matching the temperature. So in the molecular level, sometimes the water molecules probably stay close, turn into solid phase for a bit, and sometimes they're loosen up a little bit and then move around. It's a liquid a bit. So sometimes you might find it in a liquid phase. Sometimes you might find it in a solid phase. But everyone knows going from solid to liquid, liquid to solid, you have some sort of like a latent heat of fusion, exchanging heat in and out. However, because you are not one-way direction, you can still have a reversible process. Some portion of it might turn into solid, solid turn into liquid, liquid, solid. So during that process that is still reversible, the heat is also reversible. Sort of like it's still with you. It's not going anywhere. Okay? However, you notice that to have that, it seems like the temperature has to match. Otherwise, then it will go one way and then will go back. So conclusion is the heat can still flow back because the process is still reversible. But on the first case on the top, the heat that involved is already, you don't know how to bring it back because the process is irreversible. So from these two examples, that give you something now here. That give you a building block of, here we go, the best engine in the universe. Here's the key one. because the heat engine involved around about bringing the heat, right, in and out. Okay, you draw in the heat from the hot reservoir, dump out the heat from the cold reservoir. Everything has to do in cycle. Okay, you think of it this way. So that means whenever you do it in cycle, so let me draw once again the diagram that we use all the time. The engine draw in the heat, dump out the heat, perform some work, very useful one, hopefully. Yeah. Okay. No matter what you do, this is going to be the temperature at sort of like a higher one, and you are dealing with the temperature at the colder one. So there are always at least two temperatures that you have to work on for the heat engine, hot and cold. Okay. So this means you definitely have to change the temperature no matter what. There's no way that the engine can operate at a single temperature. That's not a heat engine. You want temperature differences all the time. However, you say to have a high efficiency engine, you need to minimize the amount of heat that you want to discard out, because you want to maximize the difference between the two to get the biggest amount of work. So you want the heat that involved in this one to be at least the best that you can get. So you don't want to lose this one out. Okay. So that means every time that you want to transfer the heat, we don't like the heat in the upper case, because the heat in the upper case, once you lose it, is gone. You're not going to be able to, well, I can say sort of like, it's not going to be useful to you anymore, pretty much something like that. So that's why it looks like it. If you want to transfer the heat, okay, you want that heat transfer to happen in the lower setup at constant temperature, pretty much, because you know that the heat transfer in this process is still a good heat. You're not losing it. So by not losing it, you hope that the energy is still with you, and then you're going to sort of add some other way and some other portion of your engine. I'll take that and then turn it into some useful work or something like that. So that's why the first logic is, if you want to transfer the heat, let's do it at constant temperature. So you do it during isothermal process. Here we go. That's why we have to study the isothermal process here. But as we already discussed, you still need to operate at different temperature. So you cannot avoid changing the temperature in your system. So you need to change it. So if that is the case, you need to switch, right? There is a temperature difference that you have to go through. And we say, if there is a heat involved in this one, that's bad heat. You're going to go through some irreversible process somehow, and the heat will be lost. So the best that you can get is, let's do it by preventing the heat loss during the temperature change. So whenever you want to change the temperature, we're going to do it with the adiabatic process. You guys with me now? Okay, so here's the conclusion. You want to transfer heat. It's the heat engine. So during the heat transfer sections, you want to do it using isothermal process. Remember this. PV diagram on the right. But then when you want to change the temperature, you want to change it by not exchanging any heat. You want to do it adiabatic. Cool. And you guys remember that the adiabatic curve is the curve that is steeper than the isothermal process. Yeah. The PV diagram on the right. If you can combine the heat engines, combine the thermodynamic processes between these two processes and build a heat engine, that heat engine is called Carnot's engine. And this is the best engine attainable in this universe. Yeah, I can say in this universe, this is the best. No other engines in this universe will operate at a higher efficiency than Carnot engine, which is from isothermal process and the adiabatic process. What kind of process, or what kind of sort of process that this one you have to go through? It looks like this. There we go. All right, see? All right, let's go slowly. You guys still okay with me? And having fun? This is like Saturday morning physics here. Okay, you start from A. Okay, let's start from there. And you got to go through a cycle, right? It's a heat engine. You want to run in cyclic process. So you want to draw in some heat. So A is at high temperature. So let me call this is T high temperature. But then when you want to draw in the heat, we want to do it isothermally. So that means I'm going to have to go along an isotherm. See, you have the blue line. That's your imaginary isotherm. So A to B must be on an isotherm. Nice. And during that part, let's draw in the heat. Q hot. Here we go. Take it in. Okay, they use a small h, but okay, let me use a capital H. Doesn't matter. Okay, draw in the heat. Now, once the heat is drawn in, you are at B. You want to go to a lower temperature, of course, because you must somehow, you have to dump or discard the heat. So now there is a temperature changing segment in your system. Changing the temperature, you have to do it adiabatically. So from B, you want to jump down to a lower temperature. Lower temperature is down here. That's T cold. Changing the temperature, you do it adiabatically. And it's going to be this curve right here, the green. See, remember, steeper than the isothermal line. That's adiabatic. Now you are down at point C. The temperature is lower now, okay? But you have to aim for the A because you want to go back to the A to complete the cycle. So the way to do that, of course, you have to somehow throw out the heat. During that discarding out the heat, you have to do it isothermally. So during that, I'm going to go from C to D. Isothermally means I am staying on an isotherm. And that is your bottom blue curve right there. This is the bottom isotherm, lower temperature. And during this time, I'm going to discard the heat out. Q cold. Dump it out. Once I'm at D, I'm going to have to shoot back to A because I want to complete the cycle. That means another change in temperature. I'm going to go up in temperature. During that temperature change, I'm going to do it without exchanging any heat. So I'm going to do another adiabatic process. Jump back from B back to A. Here we go. And complete the cycle. Here we go. That's it, guys. As you can see, now I have this cycle of 2 isothermal process and 2 adiabatic process. Yes. Once I combine these 4 processes into a cycle, this is the Carnot cycle. Carnot cycle, representing a Carnot engine. Very cool. All right. I think he's a French engineer doing locomotive. He's a locomotive engineer. So he's doing like, at the time you burn coal to run train. So he's sort of like thinking about how to improve the efficiency. What would be the best efficiency that you can get to pretty much, perform on the heat engine, something like that. All right, is that nice? So this is the best engine in the universe. Wow. When they say wow means, what's next? Okay, now I see it's 2 isothermal, 2 adiabatic combined into a cycle. You get an engine that's named Carnot. And what is the consequence of this? Consequence is this. All right. Bam, bam, bam. All right. We are not trying to prove anything here, but the point is, you know how to do the detailed calculations of all parts in this Carnot cycle. You know what is going on during the isothermal process. Yeah, isothermal, the work done equal to the heat flow as nRT log V final over V initial, everything, blah, blah, blah. And the For the adiabatic, you know that it's going to be PV to the gamma equal to constant. And then you can mix and match between changing the P to V, V to T, on and on. So you're going to get 4 equations that links between these 4 points, A, B, C, D, A. And once you solve this system of equations, you get one very simple conclusion. And that's what I'm going to get you to there. Yes. Isn't that nice? So today's lecture is pretty good. You don't need to solve anything. For the Carnot engine, the conclusion is the ratio between the heat that you are discarding out and the heat that you draw in from the hot reservoir is exactly equal to the ratio of the temperature of those 2 reservoirs. Done. Woo! And the good thing about this one is, now you can turn the efficiency expression that you got before, 1 minus Q cold over Q hot. This ratio is just turned into the ratio of the temperature. And that's it. You can put the subscript C for that, just to signify that this is the efficiency of a Carnot engine. Done. Done in the sense that this is the only conclusion I want to give for, well, after introducing the Carnot engine to you, and this is one attachment that you're going to get out of this. Okay, so don't worry about solving this system of equations. That's not the point. The point is this. You know how to find the highest efficiency of a heat engine that run between 2 temperatures. No engines can beat this engine, pretty much. Isn't that nice? All right, if this is nice, okay? So what I'm gonna show you, don't worry about the detail of this. This engine is the car engine, like gasolines or diesel engine and stuff. So this one, you can see that if you want to sort of explain how the engine of your car is operating under PV diagram, it might look something like this. As you can see, it's definitely not going to look like Carnot cycle, because you're going to have some maybe constant volume process, blah, blah, blah. And if you want to try to calculate the efficiency of this cycle, it's always less than the Carnot's one. That's the point. Okay, and you can try coming up with whatever process that you can imagine, or you can, you know, want to try, I want to figure out the better engine to beat this. Eventually, you're going to end up with the Carnot engine. That's the highest. That's your upper limit of the efficiency. Cool. All right, and the nice thing about this one is, let's sort of give an idea of this one. If you have 3 engines operate between reservoirs, separated by 300K, separated by 300K. So you have the scenario of 300 and 600, that's cold and hot, or 500 and 800 and 700 and 1000. So you think which one would give you the highest efficiency? What do you think? Well, Ajahn, I just calculate efficiency 1 by 1. That is fine. You can do that. For the Carnot engine, they're both Carnot. I mean, they're all Carnot engine, because we want to find the best possible. So we're going to do 1 minus T cold over T hot. Okay. So you just do 1 minus T cold. Let's get the number from part A. That's done. And then you can just keep doing this for part B. And doing this for engine C. There you go. And now you can just compare the numbers. Okay, the easiest one, of course, I mean, on top, it's 1 minus 0.7, so it's 0.3. The middle one don't need to calculate, because this one is definitely going to be 0.5. It's getting better. All right. And actually, I can give you like a one example that's going to sort of like go crazy. Let me put it like this one. If I can do engine between 0 and 300, wow, that will be number 1. So that means the colder that you can bring your temperature at the TC down, the better of the efficiency you're going to get. Is that right? Make sense? Come back here again. Look at this one. Well, Ajahn, because the Carnot engine is the best engine possible, the efficiency from this Carnot engine will be the efficiency that's you can get as high as you can get out of an engine. So if you want to get efficiency of 1, how are you going to do it? Well, then EC going to be equal to 1 when T core is 0. Absolute 0 degree degree Kelvin, that's when you're going to get the perfect 100% efficient engine, which is impossible, of course. We already know that. This is unattainable temperature. So that is once again guaranteed. There is no 100% engine in this universe. You cannot steal energy from the nature without discarding something else. Okay, so when you look at the YouTube video online and then you have like a perpetual motion of something that the system run for itself forever, that's not possible, right? There's no way. There's no perpetual thing in this universe. Something that run by itself and never stops, that's not gonna happen in this universe. Okay, and of course you can argue again, yeah, that I can find infinite temperature. Okay, that ends is never gonna happen for sure, because that infinity is, well, you don't know what's big is big, right? You can go as big as you want, but it's still not big enough. Okay, guys, so I hope you see the whole idea of what does the efficiency and all this stuff means, and there's not a lot more than just what we have done in the first law of thermodynamics. So the big portion of this segment of the lecture is pretty much the first law of thermodynamics. And today we just add on top, what does it mean by efficiency, and add on top the best efficiency engine, the highest efficiency engine possible that you're going to get when you want to running an engine between 2 temperatures is a Carnot engine. Cool. And the conclusion is very simple. The ratio between the heat discarded and the heat draw-ins is the same as the ratio of the temperature of the 2 reservoirs. All right, cool. Okay. All right. I think I'm gonna pretty much do one more explanation and we're gonna take a break here. Sounds good? I think that's a good time. And after coming back, I'm gonna show you the detailed calculations of how can we bring those techniques and the way of calculating stuff from the first law of thermodynamics, combine it with the heat engine, and answer the questions from the perspective of the efficiency of an engine. So what I'm going to stop here before the break, I'm going to try to ask you this. This is the reason why we can't charge your smartphone using your body temperature. All right, because everyone knows. I think maybe some of you have already sort of curious about this. Like, Ajahn, our body temperature is 37 degrees Celsius. Okay, that's your body temperature. Okay, and then we're losing heat all the time, of course, because maybe the room temperature is like 20 Celsius, for example. Okay, so there's a heat coming out from your body all the time. So if you want to take the temperature difference and use this temperature difference to run some engine and then turn that engine, sort of the output of that engine is like a USB charger or something like that. So you can see now, if the engine that you want to place here can draw in heat from the hot reservoir, dump heat out to the cold reservoir, and try to generate a good work. Okay, so now you can see that the highest efficiency possible is going to be the Carnot engine. This engine has to be Carnot engine. And the efficiency that you're going to get is going to be 1 minus 273 plus 20, that's T cold, divided by 273 plus 37, that's your T hot, that's your body temperature. And that would be 1 minus approximately, like I can go, okay, I can do exact actually. Here we go. Something like this. And you guys want to punch some calculator here? Yeah, I can do together. So now, if you guys curious, I'm going to come up with the numbers of this one. Yeah, I sort of try to punch again, but I already know the answer actually, approximately. All right. There you go. So this number turns out to be 0.055, let's say. So turn into a percent, it's going to be 5.5% approximately. So that means if you want to get the best out of this temperature difference, the efficiency will be only 5% maximum, 5.5. That's your upper limit. And of course, in reality, you have a friction, you have energy loss from this, from that, everywhere. So you're not going to get like even like a percent or even half a percent efficient engine out of it. And not let alone, this is just the efficiency. You haven't talked about the amount of energy that you're going to get out of this. The rate of the energy flow will be so slow. So that's why you cannot do anything much. Okay, now you start seeing why the temperature difference is so important in the heat engine, because the bigger the difference in the temperature, at least will give you a higher efficiency. That's why you have to combust the gas in your cylinder chamber in your car engine, because you want to get up to a very high temperature. And hopefully that will be the amount of energy that in there too. You want to draw it out and try to make the best out of it. Okay. Sounds reasonable? So the question about, building like a power plant using the temperature difference between maybe the surface of the ocean and the bottom of the ocean. The bottom of the ocean is low temperature. The surface temperature is maybe during the daytime is like 40 degrees Celsius, but it's just the temperature difference is so small. So the efficiency of that is going to be super, super small. And then once you add into some friction, some, loss there, loss here, you never get anything out of it. Okay, sounds sort of reasonable. Why? Well, the nature is not so kind in terms of energy. Well, not super kind. I mean, it's still kind enough. You can still use solar energy, wind energy, fossil fuel, gas, and other stuff. Right? Usually we burn. All right. Most of the energy we got is chemical. Right? We take out the chemical energy that's hidden in the molecules of this stuff. Okay, guys. I hope you learned something and they see a little bit of connections in the real world and something that we try to learn from thermodynamics. All right. After coming back, after the break, I will show you many, many examples, and we want to do the calculation of the efficiency.